When we look up at the night sky, we see thousands of tiny points of light. These are stars, and they seem incredibly far away. But the true size of the universe is so much bigger than anything we can easily imagine. In fact, the universe is so large that our human brains struggle to understand just how vast it really is. Think about the biggest thing you can imagine. Maybe it's the ocean, or a mountain range, or even the entire Earth. Now multiply that by a number so large that you would need millions of years just to count to it. You're still not even close to understanding how big the universe truly is. The universe contains everything that exists. It includes all the stars, all the planets, all the galaxies, all the empty space between them, and even time itself. When scientists talk about the universe, they mean absolutely everything that we can observe, and even things we cannot observe. To understand how big the universe is, we need to start small and work our way up. We'll begin with things we can understand, like the size of Earth, and then gradually expand our view until we're looking at the entire cosmos. Our home planet Earth is already pretty big from our perspective. If you wanted to walk around the entire equator of Earth, you would need to walk about 40,000 kilometers. That's roughly 25,000 miles. If you walked without stopping at a normal pace, it would take you more than a year of constant walking to complete this journey. The diameter of Earth, which means the distance through the middle from one side to the other, is about 12,742 kilometers. That's about 7,918 miles. To give you a sense of scale, if you could drive a car straight through the Earth at highway speed, it would take you about 6 or 7 hours of non-stop driving to get from one side to the other. Of course, you can't actually drive through Earth, but this helps us understand the size. Earth seems enormous to us because we're so small compared to it. A human being is usually between 1.5 meters and 2 meters tall. Earth's diameter is more than 6 million times larger than a tall person. If you were the size of a single cell in your body, Earth would seem as incomprehensibly large to you as the entire universe seems to us now. The Moon orbits around Earth, and it's our closest neighbor in space. The average distance from Earth to the Moon is about 384,400 kilometers. That's roughly 238,855 miles. This might not sound like much compared to Earth's size, but it's actually quite far. If you could drive a car to the Moon at highway speed without stopping, it would take you about 6 months to get there. The astronauts who went to the Moon in the Apollo missions took about 3 days to make the journey using incredibly powerful rockets. To put this in perspective, you could fit about 30 Earths side by side in the space between Earth and the Moon. The Moon itself is much smaller than Earth. Its diameter is about 3,474 kilometers, which is roughly 2,159 miles. This means the Moon is a bit more than 1/4 the size of Earth. Now we start to see distances that become truly difficult to imagine. The Sun is the star at the center of our solar system, and Earth orbits around it. The average distance from Earth to the Sun is about 150 million kilometers. This is roughly 93 million miles. Scientists use this distance so often that they gave it a special name. 1 astronomical unit, or O for short. 1 astronomical unit equals the average distance from Earth to the Sun. If you tried to drive to the Sun at highway speed, it would take you about 170 years of non-stop driving. Even light, which travels faster than anything else in the universe, takes about 8 minutes and 20 seconds to travel from the Sun to Earth. The speed of light is approximately 300,000 kilometers per second. That's about 186,000 miles per second. Nothing can travel faster than light. This speed is so fast that light can travel around the entire Earth more than 7 times in just 1 second. The Sun itself is enormous. Its diameter is about 1,392,000 kilometers. That's roughly 864,000 miles. You could fit about 109 Earths side by side across the diameter of the Sun. In fact, if the Sun were hollow, you could fit about 1,300,000 Earths inside it. The Sun contains more than 99% of all the mass in our solar system. Everything else, including all the planets, moons, asteroids, and comets combined, makes up less than 1% of the total mass. Our solar system includes the Sun and everything that orbits around it. This includes 8 planets, dozens of moons, countless asteroids, comets, and lots of dust and gas. The 8 planets, in order from closest to farthest from the Sun, are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Each planet orbits the Sun at a different distance. Mercury, the closest planet to the Sun, orbits at an average distance of about 58 million kilometers, or roughly 36 million miles. That's about 0.39 astronomical units. Venus orbits at about 108 million kilometers, or 67 million miles from the Sun. That's about 0.72 astronomical units. We already know Earth orbits at 1 astronomical unit, which is 150 million kilometers, or 93 million miles. Mars, often called the Red Planet, orbits at about 228 million kilometers, or 142 million miles. That's about 1.52 astronomical units from the Sun. Now we get to the giant planet. Jupiter, the largest planet in our solar system, orbits at about 778 million kilometers from the Sun. That's roughly 484 million miles, or about 5.2 astronomical units. Saturn, famous for its beautiful rings, orbits at about 1,430,000,000 kilometers. That's approximately 889 million miles, or 9.5 for astronomical units from the Sun. Uranus orbits at about 2,870,000,000 kilometers, which is roughly 1,784,000,000 miles, or 19.2 astronomical units. Neptune, the farthest official planet from the Sun, orbits at approximately 4,500,000,000 kilometers. That's about 2,800,000,000 miles, or 30 astronomical units from the Sun. But the solar system doesn't end at Neptune. Far beyond Neptune, there's a region called the Kuiper Belt, which contains thousands of icy objects. including the dwarf planet Pluto. Pluto orbits at an average distance of about 5,900,000,000 kilometers, or roughly 39.5 astronomical units from the Sun. Even farther out, there's a spherical cloud of icy objects called the Oort cloud. Scientists believe the Oort cloud extends from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. At its farthest edge, the Oort cloud is about 15 trillion kilometers away from the Sun. That's roughly 9,300,000,000,000 miles. If you could somehow travel at the speed of light, it would take you about 1.5 years to reach the outer edge of the Oort cloud. This region marks the true boundary of our solar system's gravitational influence. Beyond our solar system lies an enormous emptiness, and then, eventually, we reach other stars. The nearest star to our Sun is called Proxima Centauri. It's actually part of a triple star system called Alpha Centauri. Proxima Centauri is about 4.24 light-years away from us. A light-year is the distance that light travels in 1 year. Since light moves at 300,000 kilometers per second, in 1 year it travels about 9,460,000,000,000 kilometers. That's roughly 5,878,000,000,000,000 miles. So Proxima Centauri is about 40 trillion kilometers away, or roughly 25 trillion miles. This is about 268,000 times farther than the distance from Earth to the Sun. If you tried to drive to Proxima Centauri at highway speed, it would take you about 46 million years. Even traveling at the speed of light, it would take more than 4 years to get there. The fastest spacecraft ever built by humans is the Parker Solar Probe, which can reach speeds of about 190 kilometers per second. Even at this incredible speed, it would take more than 6,700 years to reach Proxima Centauri. This gives you an idea of the vast emptiness between stars. Space is called space for a good reason. There's a lot of empty space out there. There are other stars relatively close to us as well. Barnard's star is about 6 light-years away. Wolf 359 is about 7.8 light-years away. Sirius, the brightest star in our night sky, is about 8.6 light-years away, within a sphere of about 16 light-years around our Sun. There are approximately 60 stars. This might sound like a lot, but remember that this sphere has a diameter of 32 light-years, which is an enormous amount of space. If you think of stars as being the size of grapefruits, and you placed them at these correct relative distances, the nearest grapefruit would be about 4,000 kilometers away. That shows you just how empty space really is. Our Sun is just one star among hundreds of billions of stars that make up our galaxy, which we call the Milky Way. A galaxy is a massive collection of stars, gas, dust, and dark matter, all held together by gravity. The Milky Way is shaped like a flat disk with a bulge in the middle and spiral arms that curl outward. If you could look at it from above, it would look somewhat like a pinwheel or a hurricane. Our solar system is located about halfway between the center of the galaxy and its outer edge, in one of the spiral arms called the Orion Arm. The Milky Way is absolutely enormous. The disk of the Milky Way is about 100,000 light-years across. Remember, 1 light-year is about 9,460,000,000,000 kilometers. So the Milky Way is roughly 946 trillion kilometers in diameter. That's about 587 trillion miles. The disk of the Milky Way is relatively thin compared to its width. It's only about 1,000 light-years thick in most places, though it's thicker near the central bulge, reaching about 10,000 light-years thick there. If you could travel at the speed of light and started at one edge of the Milky Way, it would take you 100,000 years to reach the other edge. At highway driving speeds, it would take you about 1 billion years. The Milky Way contains an estimated 200 billion to 400 billion stars. Some recent studies suggest there might be even more, perhaps as many as 600 billion stars. Along with these stars, there are also vast clouds of gas and dust, which is where new stars are born. Our solar system orbits around the center of the Milky Way. We're traveling through space at a speed of about 828,000 kilometers per hour relative to the galactic center. That's about 514,000 miles per hour. Even at this tremendous speed, it takes our solar system about 225 million years to complete one full orbit around the galaxy. Think about that for a moment. The last time our solar system was in this exact position in the galaxy, dinosaurs hadn't even appeared on Earth yet, since Earth formed about 4.5 billion years ago. Our solar system has completed roughly 20 orbits around the Milky Way. At the very center of the Milky Way, scientists believe there's a supermassive black hole called Sagittarius, a star. This black hole has a mass equal to about 4 million times the mass of our Sun. It's so massive and its gravity is so strong that nothing, not even light, can escape once it gets too close. The Milky Way isn't alone in space. It's surrounded by numerous smaller satellite galaxies that orbit around it. The two largest of these are called the Large Magellanic Cloud and the Small Magellanic Cloud. The Large Magellanic Cloud is about 163,000 light-years away from us, and it contains roughly 30 billion stars. The Small Magellanic Cloud is about 200,000 light-years away and contains several billion stars beyond the Milky Way. Space is filled with billions upon billions of other galaxies. Each galaxy contains millions, billions, or even trillions of stars. The nearest large galaxy to the Milky Way is called Andromeda, or M31. The Andromeda galaxy is about 2.5 million light-years away from us. That means the light we see from Andromeda today actually left that galaxy 2.5 million years ago. When we look at Andromeda, we're seeing it as it was in the distant past. The Andromeda galaxy is actually larger than the Milky Way. It's about 220,000 light-years across and contains roughly 1 trillion stars. That's about 2 to 5 times more stars than the Milky Way has. Interestingly, the Andromeda galaxy is moving toward us at a speed of about 110 kilometers per second. Scientists predict that in about 4.5 billion years, Andromeda and the Milky Way will collide and eventually merge into a single, larger galaxy. Don't worry though, When galaxies collide, the stars are so far apart that very few actual collisions between stars occur. It's more like two swarms of bees passing through each other. The Milky Way, Andromeda, and more than 50 other smaller galaxies make up what astronomers call the local group. This is a collection of galaxies that are all relatively close together and bound by gravity. The local group spans about 10 million light-years across. Some of the other notable galaxies in the local group include the Triangulum galaxy, which is about 3 million light-years away and contains about 40 billion stars, and several small dwarf galaxies with names like Draco Dwarf, Leo I, and Sculptor Dwarf. Beyond the local group, there are galaxy groups and clusters everywhere we look. A galaxy cluster is a collection of hundreds or thousands of galaxies, all held together by gravity. The nearest large galaxy cluster to us is called the Virgo cluster. It's about 55 million light-years away and contains approximately 1,500 galaxies. The Virgo cluster is enormous, spanning about 15 million light-years across. Our local group is actually on the outskirts of an even larger structure called the Virgo supercluster. A supercluster is a massive collection of galaxy clusters. The Virgo supercluster contains approximately 100 galaxy groups and clusters, including our local group and the Virgo cluster. The Virgo supercluster spans roughly 110 million light-years across and contains about 47,000 large galaxies. But even that's not the end. In 2014, scientists discovered that the Virgo supercluster is actually part of an even more massive structure they named Laniakea, which means immeasurable heaven in Hawaiian. Laniakea is a supercluster of superclusters, containing about 100,000 galaxies. It spans about 520 million light-years across. To put this in perspective, if Earth were the size of a grain of sand, the Laniakea supercluster would be larger than the orbit of Neptune. As we zoom out further and further, we eventually reach a limit to what we can see. This limit exists not because there's nothing beyond it, but because light from farther away hasn't had enough time to reach us yet. The universe began with an event we call the Big Bang, which happened approximately 13.8 billion years ago. Before the Big Bang, there was no space, no time, no matter, nothing at all as we understand it. Then, in an instant, space itself began expanding, and all the matter and energy that would eventually form stars, galaxies, and everything else came into existence. Since the Big Bang happened 13.8 billion years ago, you might think we can only see objects that are 13.8 billion light-years away. But it's more complicated than that. Space itself has been expanding this whole time, carrying galaxies away from each other. Objects that emitted light toward us shortly after the Big Bang have now moved much farther away due to this expansion. When scientists calculate how far we can see, taking into account the expansion of space, they find that the observable universe is a sphere about 93 billion light-years across. That's the diameter from one edge of what we can see to the opposite edge, passing through Earth. The radius of the observable universe, which is the distance from us to the edge in any direction, is about 46.5 billion light-years. This equals approximately 440 billion trillion kilometers, or about 273 billion trillion miles. If you could travel at the speed of light, it would take you 46.5 billion years to reach the edge of the observable universe. But here's something mind-bending. By the time you got there, the universe would have expanded so much that the edge would have moved even farther away. The observable universe contains an estimated 2 trillion galaxies. Let me write that number out. 2,000 billion galaxies. Each of these galaxies contains millions, billions, or trillions of stars. If we assume an average of 100 billion stars per galaxy, that means the observable universe contains approximately 200 billion trillion stars. That's a 2 followed by 23 zeros. 200,000 billion stars. To give you some perspective on this number, there are more stars in the observable universe than there are grains of sand on all the beaches on Earth. In fact, there are probably more stars than there are grains of sand on Earth and all the other rocky planets in our solar system combined. You might be wondering how scientists can possibly know these enormous distances. After all, we can't just take a ruler to space. Scientists use several clever methods to measure distances in space, and different methods work better for different distance ranges. For nearby objects in our solar system, scientists can use radar. They bounce radio waves off planets and measure how long it takes for the signal to return. Since radio waves travel at the speed of light, they can calculate the distance. This method works well for measuring distances within our solar system. For nearby stars, astronomers use a method called parallax. Hold your finger out in front of you and look at it with just your left eye, then just your right eye. Notice how your finger appears to shift position against the background. That's parallax. Astronomers do something similar with stars. They measure the position of a nearby star against distant background stars, then wait 6 months and measure again. 6 months later, Earth has moved to the opposite side of its orbit around the Sun. So we're looking at the star from a different angle, about 300 million kilometers away from where we were before. By measuring how much the star appears to shift and using some mathematics, astronomers can calculate how far away the star is. This parallax method works well for stars up to a few thousand light years away. Beyond that, the shift becomes too small to measure accurately, even with our best telescopes. For more distant objects, astronomers use what they call standard candles. These are objects whose true brightness is known. By comparing how bright they appear from Earth with how bright they actually are, astronomers can calculate how far away they must be. One type of standard candle is a special kind of star called a Cepheid variable. These stars pulse regularly, getting brighter and dimmer in a predictable pattern. Scientists discovered that the period of this pulsing is directly related to how bright the star actually is. By measuring the period and comparing it to how bright the star appears, they can determine its distance. Cepheid variables can be used to measure distances up to about 100 million light-years away. Beyond that, they become too faint to observe clearly. For even greater distances, Astronomers use exploding stars called supernova, a particular type called type Ia supernova always explodes with roughly the same brightness. These explosions are so bright that they can be seen from billions of light years away. By measuring how bright a type Ia supernova appears, astronomers can calculate its distance. For the most distant objects in the universe, astronomers use the expansion of space itself as a measuring tool. Because space is expanding, distant objects are moving away from us. The farther away something is, the faster it's moving away. This makes the light from distant objects shift toward the red end of the spectrum, an effect called redshift. By measuring how much an object's light has been redshifted, astronomers can determine both how fast it's moving away and how far away it is. This method works for objects billions of light years away. All of these methods build on each other like rungs on a ladder, which is why astronomers call this system the cosmic distance ladder. Each method is calibrated, using objects whose distances we've measured with the previous method. One of the most important discoveries in understanding the size of the universe was made in 1929 by an astronomer named Edwin Hubble. He discovered that the universe is expanding. Galaxies are moving away from each other, and the farther apart they are, the faster they're moving apart. This doesn't mean galaxies are flying through space away from some central point. Instead, space itself is expanding. Imagine the universe as the surface of a balloon, with galaxies as dots on that surface. As you blow up the balloon, every dot moves away from every other dot, but none of the dots are actually moving across the balloon's surface. The surface itself is expanding, carrying the dots with it. The rate at which the universe is expanding is described by something called the Hubble constant. Scientists are still working to measure this precisely, but current estimates suggest that space is expanding at about 70 kilometers per second per minute. Let me break that down. A parsec is a unit of distance equal to about 3.26 light years, or roughly 30 trillion kilometers. A megaparsec is 1 million parsecs. So the Hubble constant tells us that for every 3.26 million light years of distance, objects are moving apart at an additional 70 kilometers per second. This means two galaxies that are 3.26 million light-years apart are moving away from each other at 70 kilometers per second. Two galaxies that are twice as far apart at 6.52 million light-years are moving apart at 140 kilometers per second. The farther apart objects are, the faster they're moving apart. This expansion of space has been happening since the Big Bang, and it's actually speeding up. In 1998, astronomers discovered that the universe's expansion is accelerating. Something is pushing space apart faster and faster, and scientists call this mysterious force dark energy. Nobody knows exactly what dark energy is, but we know it makes up about 68% of all the energy in the universe. Regular matter, the stuff that makes up stars, planets, and us, makes up only about 5% of the universe. The remaining 27% is something called dark matter, which we also don't fully understand. Dark matter doesn't emit light or energy, but we know it exists because we can see its gravitational effects on regular matter. This means that 95% of the universe is made of things we don't fully understand yet. We can only directly observe and study 5% of what's out there. The observable universe is just the part of the universe we can see. But the actual universe is almost certainly much larger than this. Remember, we can only see light that has had time to reach us since the Big Bang. But space extends beyond this observable limit. The universe could be just slightly bigger than what we can see, or it could be infinitely large. We simply don't know. Some scientists think the universe might be infinite, going on forever in all directions. If that's true, then asking how big is the universe would be like asking what's the biggest number. There wouldn't be an answer because it just keeps going. Other scientists propose that the universe might be finite but unbounded. This is a tricky concept to understand. Imagine walking on the surface of the Earth. You can walk in a straight line forever and never reach an edge or boundary. Yet Earth's surface is finite. It has a specific area. In a similar way, the universe might be curved in higher dimensions, so that it has no edge, but still has a finite size. Another possibility is that our universe is just one of many universes in a multiverse. In this scenario, there could be countless other universes, each with its own physical laws, existing separately from ours. These other universes would be completely unreachable. We couldn't observe them or travel to them. This is a fascinating idea, but it's very difficult or impossible to test scientifically. Some versions of multiverse theory suggest that our universe is one bubble in an eternally inflating space, where new universe bubbles are constantly forming. In this model, the total size of all existence would be infinite. The honest answer is that we do and know how big the universe truly is beyond what we can observe. It might be that we'll never know because the information is simply unreachable to us. Let's try to put all of this in perspective by comparing different scales. If Earth were the size of a grain of sand, the Sun would be about the size of a ping-pong ball, located about 3 meters away. Neptune, the farthest planet, would be about 90 meters away, roughly the length of a soccer field. On this scale, the nearest star, Proxima Centauri, would be about 800 kilometers away, roughly the distance from New York to Atlanta, or from London to Hamburg. That's how empty space is between stars. The Milky Way galaxy on this scale would be about 25 million kilometers across. That's about 65 times the distance from Earth to the Moon in reality. The Andromeda galaxy would be about 600 million kilometers away on this scale. That's roughly the actual distance from the Sun to Jupiter. The observable universe on this scale would be about 56 billion kilometers across, which is larger than the real distance from the Sun to Neptune, about 4.5 billion kilometers, but still incomprehensibly vast. Let's try another way to understand these scales. Imagine you could travel at the speed of light, the fastest speed possible. Here's how long it would take you to reach various destinations. To the Moon, 1.3 seconds. To the Sun, 8.3 minutes. To Neptune, 4 hours to the edge of the solar system, Oort cloud. 1.5 years to the nearest star, 4.2 years. Across the Milky Way galaxy, 100,000 years to the Andromeda Galaxy, 2.5 million years to the edge of the Observable Universe, 46.5 billion years, remember. These times are at the speed of light, which is about 1 billion kilometers per hour. Nothing can travel faster than this speed. With our current technology, we can't even come close to light speed. The fastest spacecraft we ever built can travel at about 1,200 times slower than light. At that speed, reaching the nearest star would take about 5,000 years. The universe wasn't always this big. It started infinitely small and has been expanding ever since the Big Bang 13.8 billion years ago. In the very first fraction of a second after the Big Bang, something extraordinary happened called cosmic inflation. The universe expanded incredibly rapidly, much faster than the speed of light. This might sound impossible, since nothing can travel faster than light. But remember that it's space itself that was expanding, not objects moving through space. Space can expand as fast as it wants during inflation, which lasted only about 1/trillionth of a trillionth of a trillionth of a second. The universe grew from smaller than an atom to about the size of a grapefruit. That might not sound like much, but it was an increase in size by a factor of about 10 to the power of 26. That S1 followed by 26 zeros. After inflation ended, the universe continued expanding at a more leisurely pace. In the early universe, everything was incredibly hot and dense. It was so hot that atoms couldn't even form. Matter existed as a soup of subatomic particles. As the universe expanded, it cooled. After about 380,000 years, it had cooled enough for the first atoms to form. This was mostly hydrogen and helium, the simplest elements. The universe became transparent to light for the first time. We can actually observe this light today. It's called the cosmic microwave background radiation, and it fills all of space. It's like a baby picture of the universe, showing us what conditions were like when the universe was just 380,000 years old. This light has been traveling through space for more than 13.4 billion years, and it's been stretched by the expansion of space from visible light into microwave radiation. After atoms formed, gravity began pulling matter together. Regions that were slightly denser than average attracted more matter, becoming denser still. Over millions of years, these dense regions collapsed to form the first stars. About 100 to 200 million years after the Big Bang. These early stars were massive and short-lived. When they died in spectacular supernova explosions, they scattered heavier elements into space. These heavier elements were incorporated into the next generation of stars. This process repeated over and over, creating all the elements we see around us today. Stars grouped together into galaxies, and galaxies grouped into clusters and superclusters, forming the large-scale structure we observe today. This process took billions of years. Our Sun formed about 4.6 billion years ago from a cloud of gas and dust that contained elements from previous generations of stars. The planets, including Earth, formed from the leftover material around the young Sun. The universe has been expanding this whole time, and as we discovered in 1998, This expansion is actually accelerating. Billions of years from now, the universe will be much bigger than it is today, and the distances between galaxies will be even more enormous. If the universe continues expanding and accelerating as it is now, what will the future look like? In the relatively near future, on cosmic timescales, the Milky Way and Andromeda galaxies will collide and merge. As I mentioned earlier, this will happen in about 4 to 5 billion years. The resulting merged galaxy is sometimes called Milkomada or Milkdromeda. Other nearby galaxies in the local group will likely merge with this new megagalaxy as well. But beyond our local group, things will look very different. As the universe continues to expand and accelerate, distant galaxies will move away from us faster and faster. Eventually, they'll be receding so fast that light from them can never reach us. In about 150 billion years, all the galaxies beyond our local group will have disappeared from view. An astronomer living in that distant future would look out at the universe and see only the merged remains of the local group galaxies. The rest of the observable universe would appear completely empty. They might conclude that they live in a universe containing only a single galaxy surrounded by infinite emptiness. This is a bit eerie to think about. If we didn't happen to live in this particular era when distant galaxies are still visible, we might never have discovered that the universe is expanding, or that there are billions of other galaxies beyond our own. As time goes on, things continue to get more spread out. The stars in our merged galaxy will eventually run out of fuel and die. The last stars will fade away about 100 trillion years from now. After that, the universe will be a cold, dark place with dead stars, black holes, and scattered particles spread across ever-increasing distances. Even black holes don't last forever. Through a process called Hawking radiation, black holes very slowly evaporate. The largest black holes will take an incomprehensibly long time to evaporate, completely about 10 to the power of 100 years. That's a 1 followed by 100 zeros. After the black holes are gone, the universe will consist mainly of photons of light, widely separated particles, and empty space. The universe will continue expanding forever, getting colder, darker, and more empty. This scenario is called the heat death of the universe. This is all very far in the future and depends on our current understanding of physics being correct. There might be things we don't know yet that could change this picture. We've mostly talked about the size of the universe in terms of distance, but there are other ways to think about scale. One way is to consider the number of atoms in the universe. The observable universe contains approximately 10 to the power of 80 atoms. That's a 1 followed by 80 zeros. This number is so large it's almost meaningless to our brains. But let me try to give you some context. There are about 7 octillion atoms in a typical human body. That's 7 billion atoms, or 7 followed by 27 zeros. The universe contains roughly 10 trillion times more atoms than are in your body. Another way to think about scale is in terms of mass. The total mass of the observable universe is estimated to be about 10 to the power of 53 kilograms. Most of this mass is in the form of dark matter, which we can't see directly. The visible matter, stars, gas, dust, and everything else we can observe, makes up only about 1/5 of the total mass. We can also consider the energy content of the universe. Einstein showed us that mass and energy are equivalent through his famous equation E equals mc squared. Here, E is energy, m is mass, and c is the speed of light. Since the speed of light is such a large number, and we're squaring it, even a small amount of mass equals an enormous amount of energy. The total energy in the observable universe, including both mass energy and dark energy, is approximately 10 to the power of 70 joules. A joule is a unit of energy. To put this in perspective, a typical lightning bolt contains about 1 billion joules. The observable universe contains about 10 to the power of 61 times more energy than that. When we look at distant objects in space, we're also looking back in time. This is because light takes time to travel. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star, you see it as it was 4 years ago. When we look at the Andromeda galaxy, we see it as it was 2.5 million years ago, when early humans were just beginning to use stone tools. The light we're seeing today was just leaving Andromeda. When we look at extremely distant galaxies, we see them as they were billions of years ago, when the universe was much younger. The farthest galaxies we've observed are so distant that we see them as they were about 13.5 billion years ago, just a few 100 million years after the Big Bang. These early galaxies look very different from modern galaxies. They're smaller, less organized, and contain fewer heavy elements, because not many generations of stars had lived and died yet. The James Webb Space Telescope, which began operating in 2022, has been observing some of these extremely distant early galaxies. It's giving us an unprecedented look at what the universe was like when it was young. In a sense, by looking out in space, we can see the entire history of the universe. We can observe galaxies at all different stages of development, from the very young to the very old. It's like having a time machine that only works in one direction. We can look back at the past, but not visit it. This also means that the observable universe has a kind of time dimension built into it. The edge of the observable universe isn't just far away in space. It's also far away in time. When we say the observable universe is 93 billion light-years across, we're describing both a spatial extent and a temporal one. One interesting way to appreciate the size of the universe is to compare the very large with the very small. A typical atom is about 1/10 of a nanometer across. A nanometer is 1/1000th of a meter. So, an atom is roughly 0.000000000001 centimeters in size. A human being is roughly 170 centimeters tall on average. This means a human is about 1 trillion times larger than an atom. Now, the observable universe is about 93 billion light-years across, which is approximately 880 billion trillion kilometers, or 88 octillion centimeters. If we compare the size of a human to the size of an atom, and then compare the size of the observable universe to the size of a human. Which ratio is bigger? It turns out that the observable universe is far, far larger compared to a human than a human is compared to an atom. The universe is about 10 to the power of 29 times the size of a human, while a human is only about 10 to the power of 12 times the size of an atom. In other words, a human is about halfway between the size of an atom and the size of the entire observable universe on a logarithmic scale. But in absolute terms, the universe is incomparably larger. Looking at it another way, if you could shrink the observable universe down to the size of Earth, a single galaxy would be smaller than a grain of pollen. On that same scale, our solar system would be far too small to see, even with the most powerful microscope. These comparisons help us understand that the universe operates on scales both larger and smaller than we can truly comprehend. We exist somewhere in the middle, able to think about both the very small and the very large, but unable to directly experience either extreme. This is a fascinating question that scientists and philosophers have pondered for a long time. There are several ways to think about it. From one perspective, the universe might need to be this big for us to exist at all. Stars need time to form, live, and die before they can create the heavy elements necessary for planets and life. The universe needs to be at least several billion years old for this process to occur. And because the universe has been expanding this whole time, being several billion years old means being tens of billions of light years across. This is sometimes called the anthropic principle. The universe has the properties it does because, if it were significantly different, we wouldn't be here to observe it. From another perspective, the universe might be big simply because there's no reason for it to be small. After the Big Bang and cosmic inflation, the universe was set on a path of expansion, and that expansion has continued ever since. Why would it stop or stay small? The universe is big because it started expanding and kept going. Some physicists think about this question in terms of the fundamental constants of nature. These are numbers like the speed of light, the strength of gravity, and the rate of cosmic expansion. In our universe, these constants have specific values, but theoretically, they could have had different values. If these constants were even slightly different, the universe might look completely different. Stars might not be able to form, or they might burn out too quickly for planets to develop life. The universe might have collapsed back on itself shortly after the Big Bang, or it might have expanded so quickly that matter could never have clumped together to form galaxies. Our universe seems to have constants that are just right for allowing complexity and life to develop. Some scientists think this might be a coincidence. Others think there might be an infinite number of universes with different constants, and we naturally find ourselves in one where the constants allow for our existence, because we couldn't exist in the others. This is all speculative, and we may never know the definitive answer to why the universe is the size it is. But the question itself reveals something important about human curiosity. We don't just want to know how big things are. We want to understand why. Despite all we've learned about the size of the universe, there's still much we don't know. In fact, the more we learn, the more we realize how much we don't know. We don't know if the universe is finite or infinite. We don't know what dark matter and dark energy really are, even though they make up 95% of the universe. We don't know if there are other universes beyond our own. We don't know what, if anything, existed before the Big Bang, or if that question even makes sense. We also face fundamental limits on what we can know. Because the universe is expanding, there are regions of space that are moving away from us faster than light can travel. We will never be able to observe these regions, no matter how long we wait or how good our technology becomes. As time goes on and the expansion accelerates, more and more of the universe will slip beyond this limit. In the far future, less and less of the universe will be observable. This means that future civilizations, if any exist, will have access to less information about the cosmos than we do. In this sense, we reliving in a special time in cosmic history, a time when much of the universe is still visible to us. But we've developed technology advanced enough to observe it. If we'd evolved billions of years later, we might never have discovered that the universe is expanding or that other galaxies exist. There are also theoretical limits to what we can know based on the laws of physics themselves. Quantum mechanics tells us that there are fundamental uncertainties in how precisely we can measure certain properties of particles. General relativity suggests that there are regions of space-time, like the inside of black holes, that are forever cut off from our observation. These limits don't mean we should stop trying to learn more. Every answer leads to new questions, and the process of discovery itself is valuable. But it does mean we should be humble about our knowledge and recognize that there may always be mysteries beyond our grasp. It's worth reflecting on how much our understanding of the universe's size has changed over human history. For most of human existence, people thought the Earth was the entire world. The sky was something separate, perhaps a dome or sphere surrounding the Earth. The stars were lights attached to this sphere, and the sun and moon moved across it. Ancient Greek philosophers were the first to suggest that Earth might be a sphere floating in space, but they still thought it was the center of everything. They developed models where the moon, sun, planets, and stars all orbited around Earth on invisible spheres. In the 1500s, Nicolaus Copernicus proposed that the sun, not Earth, was the center of the solar system. This was revolutionary, but he still thought the stars were fixed on a distant sphere surrounding the solar system. In the early 1600s, Galileo Galilei used a telescope to observe the heavens and found moons orbiting Jupiter. This provided evidence that Earth wasn't the center of everything. He also observed that the Milky Way, that hazy band of light across the night sky, was actually made up of countless individual stars. Throughout the 1700s and 1800s, astronomers realized that the stars were at vastly different distances from us, not all on one sphere. They began to understand that space was three-dimensional and much larger than previously imagined. In the early 1900s, astronomers still thought the Milky Way was the entire universe. They could see fuzzy patches of light called nebulae, but they thought these were clouds of gas within our galaxy. In that, Edwin Hubble used the largest telescope of his time to observe one of these nebulae, the Andromeda Nebula. He discovered that it was actually a separate galaxy far outside the Milky Way. Suddenly, the known universe became millions of times larger. Just 5 years later, in 1929, Hubble discovered that the universe was expanding. This led to the development of the Big Bang Theory and our modern understanding of cosmic history. Throughout the 20th and 21st centuries, astronomers have continued discovering that the universe is larger and more complex than we thought. We've discovered dark matter, dark energy, the acceleration of cosmic expansion, and billions upon billions of galaxies. Each time we've developed better technology, we've discovered that the universe is bigger than we imagined. First telescopes, then larger telescopes, then telescopes in space, then space telescopes that can see in different wavelengths of light. Each advance has revealed more. This history teaches us humility. Every generation thought they had roughly figured out the universe's size, only for the next generation to discover it was much larger. It's quite possible that future generations will discover the universe is even larger than we currently think. The enormous size of the universe raises some profound questions and has some interesting implications for how we think about our place in the cosmos. One immediate implication is that we're probably not alone. The observable universe contains about 2 trillion galaxies, each with billions or trillions of stars. Many of these stars have planets. Even if life is extremely rare, the sheer number of planets suggests that life probably exists elsewhere. Scientists estimate there may be 40 billion Earth-sized planets in the habitable zone of their stars, just in the Milky Way galaxy alone. The habitable zone is the region around a star where conditions might be right for liquid water to exist on a planet's surface. If even a tiny fraction of these planets developed life, and if a tiny fraction of those developed intelligent life, there could still be thousands or millions of other civilizations in our galaxy alone. And there are 2 trillion galaxies in the observable universe. However, the enormous distances between stars also mean that contact with alien civilizations might be impossible. Even if another civilization existed on a planet orbiting the nearest star, Proxima Centauri, it would take more than 4 years for a radio message to reach them, and another 4 years to get a reply, and that's the nearest star. Most stars are much, much farther away. The vastness of space essentially creates a quarantine, unless faster than light travel is possible, which current physics says it isn't. Civilizations are likely forever isolated from each other. This isolation might actually be a good thing. It means that even if there are hostile alien civilizations out there, they probably can't reach us. The distances are simply too great. The size of the universe also gives us perspective on our own significance. Earth is a tiny dot orbiting an average star in an average galaxy among billions of others. In the grand scheme of things, we're incredibly small and seemingly insignificant. But there's another way to look at it. Despite being so small, we're able to understand and appreciate the vast universe around us. We can measure distances across billions of light years. We can figure out what stars are made of and how they work. We can trace the history of the cosmos back to a fraction of a second after the Big Bang. The fact that matter can organize itself into complex patterns that can think, feel, and understand the universe itself is remarkable. In a sense, through us, the universe is becoming aware of itself. We're also significant in the sense that we might be rare. Life might be common in the universe, or it might be incredibly rare. If it's rare, then every living thing on Earth represents something precious. If intelligent life is even rarer, then humanity might be one of very few examples of matter organizing itself into something that can contemplate its own existence. The size of the universe also reminds us of how much we have yet to learn. We've studied Earth in great detail, and we're beginning to explore our solar system. But we've barely scratched the surface of understanding our galaxy, let alone the billions of other galaxies beyond it. There are likely discoveries waiting out there that we can't even imagine yet. New types of objects, new phenomena, maybe even new laws of physics that only become apparent at certain scales or in certain conditions. One of the biggest unanswered questions about the universe's size is whether it's finite or infinite. This is a question that has puzzled humans for thousands of years. If the universe is finite, that means it has a specific, definite size. It might be larger than the observable universe, perhaps much larger, but there would be some number that describes how big it is. If the universe is infinite, it goes on forever in all directions. There's no edge, no boundary, no end. In an infinite universe, every possible arrangement of matter that doesn't violate the laws of physics would exist somewhere. In fact, in a truly infinite universe, every possible arrangement would exist infinitely many times. This has some mind-bending implications. If the universe is infinite, then somewhere out there, there's another Earth exactly like ours. In fact, there would be infinitely many of them. There would be an Earth where everything is exactly the same as our Earth up until this moment. But tomorrow something different happens. There would be an Earth where you were never born. There would be an Earth where dinosaurs never went extinct. Every possible variation would exist somewhere, infinitely far away. This seems almost too strange to be true, but it is a logical consequence of a truly infinite universe, combined with a finite number of ways that matter can be arranged. However, most scientists are skeptical of this conclusion. Even if the universe is infinite, the laws of physics might constrain matter in ways that make certain arrangements impossible or extremely unlikely, even given infinite space. So how can we determine if the universe is finite or infinite? Scientists look at the geometry of space itself. Einstein's theory of general relativity tells us that space can be curved. It can have positive curvature, like the surface of a sphere, negative curvature, like a saddle, or no curvature, flat, like a sheet of paper. If space has positive curvature, the universe is finite, like the surface of a sphere. If space has negative curvature, or is flat, the universe could be infinite, though it might also be finite with a more complex shape. By studying the cosmic microwave background radiation that light from when the universe was 380,000 years old, Scientists can measure the curvature of space. So far, all measurements suggest that space is very close to being flat. This means the universe could be infinite, or it could be finite but very large. The truth is, we might never know for certain whether the universe is finite or infinite. If it's infinite, we can never observe all of it to confirm. If it's finite but much larger than the observable universe, we also can't observe enough of it to measure its total size. This is one of those fundamental questions that might remain forever unanswered, at least with our current understanding of physics. We journeyed from the familiar size of Earth to the incomprehensible vastness of the observable universe and beyond. We've seen that the universe is at least 93 billion light-years across, containing 2 trillion galaxies with hundreds of billions of trillions of stars. We've learned that the universe started infinitely small and has been expanding for 13.8 billion years. We've seen how this expansion is accelerating, driven by mysterious dark energy. We've explored how scientists measure these vast distances and how our understanding has evolved over centuries. But we've also confronted the limits of our knowledge. We don't know if the universe is finite or infinite. We don't know what most of the universe is made of. We don't know if there are other universes beyond our own. In some ways, the question, how big is the universe, doesn't have a simple answer. The observable universe has a definite size, 93 billion light-years across. But the actual universe, beyond what we can observe, we simply don't know. This uncertainty might seem frustrating, but it's also exciting. It means there's still so much to discover. Every generation of humans has expanded our understanding of the cosmos, and there's no reason to think we've reached the end of that process. The size of the universe is almost impossible for us to truly comprehend. Our brains didn't evolve to understand scales ranging from subatomic particles to billions of light-years. We can work with the numbers and create analogies, but we can't really feel or visualize what these distances mean. Yet we try. We build bigger telescopes, develop new theories, and push the boundaries of our knowledge. We do this because we're curious. We want to know where we came from, where we're going, and what else is out there. The vast size of the universe might make us feel small and insignificant. And in a physical sense, we are incredibly tiny compared to the cosmos. But we're also significant in our ability to ask these questions, to seek answers, and to appreciate the beauty and mystery of existence. We live on a small planet orbiting an ordinary star in a typical galaxy among billions. But we're able to look out at all of this, to measure it, to understand it, and to wonder about it. That's not insignificant at all. That might be the most significant thing in the universe. As we continue to explore, we'll likely discover that the universe is even larger and more complex than we currently imagine. New technologies, like more powerful space telescopes and more sensitive detectors, will reveal more distant objects and help us peer further back in time. We might find evidence for or against an infinite universe. We might discover new physics that changes our understanding of space, time, and expansion. We might detect signs of life on other worlds, or even signals from other civilizations. Or we might find that some questions remain forever unanswered, hidden behind the horizons of what's observable or understandable. Either way, the question, how big is the universe, will continue to drive human curiosity and scientific advancement. It is a question that connects us to the cosmos and reminds us that we are part of something much larger than ourselves. The universe is at least 93 billion light-years across. It contains at least 2 trillion galaxies. It's at least 13.8 billion years old, but it might be much larger in ways we haven't yet discovered. The true answer to how big is the universe might be bigger than we can know, but not bigger than we can imagine. And that's a beautiful thing.